Hello, my name is Erica Podest, and this is the second webinar of the SAR webinar series. The focus of this presentation is SAR processing and data analysis. So this presentation will be focused on using data from the European Space Agency's Sentinel-1 satellite, which has a C-band SAR. Its satellite is currently operational and the data is freely available. And the SAR processing steps learned here can be applied to other SAR data sets. So the learning objectives are to understand Sentinel-1 data, learn what are the necessary pre-processing steps, and we'll do a little bit of data analysis. In order to meet those learning objectives, I'll provide background about Sentinel-1 data and show you how to access, open, and display the data. We will go through the necessary pre-processing steps and then do a small analysis where we'll be identifying open water from everything else. So we'll start with the Sentinel-1 background. This table shows the characteristics of several SAR sensors, and the column highlighted in green is what you should note. This contains a summary of the characteristics of Sentinel-1. As mentioned, this is a C-band SAR with either a VV and VH or HH and HV polarizations. It depends on which mode you're using, which we'll cover next. So it's important for you to know that there are two Sentinel-1 satellites in orbit, and they both have the same sensor characteristics. So one is Sentinel-1A, which was launched in early April 2014, and the other one is Sentinel-1B, which was launched 2 years later in late April 2016. So each satellite has a 12-day temporal repeat, and the two, therefore, provide a 6-day temporal repeat. The Sentinel-1 data can be freely accessed online. So Sentinel-1 has 4 different modes of acquisition. The first mode is the extra wide swath mode, and that's primarily for monitoring oceans and coasts. It has a 400-kilometer swath and a spatial resolution of 25 by 40 meters. Then there is strip mode, which is special order only, and that has an 80-kilometer swath, 5 by 5 meter spatial resolution. Then there's the wave mode, which is routinely collected for the oceans, and that has a 20-kilometer swath, 5 by 5 meter spatial resolution. And then finally, we have the interferometric wide swath, which has routine collections over land, has a 250-kilometer swath, and a spatial resolution of 5 by 20. So how do you access the Sentinel-1 images? There are 2 ways to access Sentinel-1. One is through the Alaska Satellite Facility, and the other one is through the European Space Agency portal, the Copernicus portal. For both, you have to register in order to be able to log in. But again, once you register, the data access is free. So there are 3 levels of data. One is the level 0, the other one is the level 1, and the other one is the level 2. So the level 0 is the raw data, which needs to be decompressed and processed. Level 1 is produced as SOC or GRD. So the SOC product preserves the phase information. So if you're doing something like interferometric SAR, then you want to use the SOC product. And there will be a webinar just focused on interferometric SAR, also known as INSAR, and that's going to be the last webinar of this webinar series. The GND product is projected to the ground range using an Earth ellipsoid and is multi-looked. So the phase information is lost in the GND product. Then you've got the file name, which contains important information about the characteristics of the file. And it's a very long file name. But if you want to know when your image was acquired, you just need to look at the file name to infer that sort of information. So it gives you information about whether it was obtained by Sentinel-1A or 1B, the swath type, the product type, polarization, day of acquisition, day and time of acquisition, orbit number, file extension. So all of that, and that's why it's so long. The Sentinel-1 Toolbox is a free and open source software developed by ESA for processing and analyzing radar images from the Sentinel series of satellites, including Sentinel-1 SAR, and SAR data from other satellites as well. So the tool includes tools for calibration, speckle noise, terrain correction, mosaic production, polarimetry, interferometry, data analysis, and classification. So it's a really, really great resource, and it's a very straightforward to use. And we'll be using the Sentinel Toolbox in this exercise. It can be accessed through the link provided here. And it's also free of charge. So the next part will cover accessing, opening, and displaying SAR data, Sentinel SAR data. So first of all, as mentioned, you can access the data through the Alaska Satellite Facility or through the ESA Copernicus portal. In this example, we'll be using the Alaska Satellite Facility's data portal. And so you copy this link, and we'll go to the data portal. Okay, so we'll go to the Alaska Satellite Facility data portal, and this is what's going to pop up. So you select a search by geographic region, and here in option 2, you'll enter the coordinates that were provided in the PowerPoint chart. So this is the area of interest. And this area of interest is located in the Amazon. It's around the city of Manaus, which is a large city in Brazil, in the Brazilian Amazon. So you'll input that in, just copy and paste, and then you'll you'll define the dates of interest, and that would be from April 25th, 2015, start date, through April 29th, 2015, end date. And then finally, down here, you specify which data set you're interested in. So we'll select Sentinel-1A and Sentinel-1B. However, note that there is a list of other SAR data sets here available in case you are interested in using data sets that were collected in the past. So you've got not only the name of the radar data set, right, but you've also got the range, the time range, right? So SMAP, there's UAV SAR, which is an airborne sensor over select areas around the world. There's ALOS pulsar data collected from 2006 to 2011. They all have different characteristics, so you'll have to go and look at how these different sensors are characterized. But this is a really great resource for those interested in using SAR data from the past. Okay, so we'll select search. And when you select search, you'll come up with the results here. And it says that it found 3 results for our area of interest and our time frame of interest. And these are the 3 images that it found that somehow cover that area of interest, right? So if you put your cursor over the thumbnail here, you can see on the display which image that belongs to, which area that belongs to. So this image is the bottom one, this is the middle one, and then if you click on it, you'll find more information, more specific information about the image. So we just clicked on the middle image, and you can find details such as the date of acquisition, the beam mode, the path frame, ascending or descending. That's very important to always keep into account whether it's ascending or descending, because the viewing geometry is different whether the path is descending or ascending, and you always want to treat these separately, especially if you're doing something like a multi-tempo analysis. You'll want to, for example, run classifications on descending or ascending images separately and then compare the final results. All right, so it tells you the polarization, frequency, it's C-band. And one thing that you'll probably want to select with Sentinel, depending on whether you're interested in different types of land cover applications, you want to go with the IW images, okay? And you also want to go with the ones that are already in ground range, so GRD HD. So you'll download this image, okay? And note that it's quite large. It's 1 gigabyte, so it might take a while. Unfortunately, you don't have the capability here with this tool to do the processing on the cloud, so you have to download the images onto your computer. Okay, so once you have it downloaded, then you go ahead and you open your Sentinel toolbox. And you just click on the icon, on the Sentinel toolbox icon. It says Snap to open, to launch the application. And you go to File, Open Product, and you select the file that was downloaded. It's usually, you have to check the default on your computer where your downloads go. It might go to your download folder or your desktop or wherever you've specified. So here, this is the file. One thing to note is that you do not want to open up the zip file previously, okay? So you don't want to uncompress the zip file. Just tell the Sentinel toolbox where that zip file is, and it'll take care of decompressing it, okay? So you just select the .zip file and you open. Okay, so that file is now open here on the very top. All of the files that you process and open will be placed here in this window called Product Explorer in the top left on the very top. Okay, so if you open that file, it's got a number of different directories in there. And if you want to, for example, find more details about your data set, you open up the abstracted metadata file, which contains lots of information about that specific file. Corner lat longs, it's a descending paths, polarization, resolution. So if you want to know extra information about your file, you can obtain it here. And if you want the whole range of detailed information about your file, you open up the original product metadata. But the important thing is the actual data itself. So we'll close this and we'll open. So we've got two polarizations. We've got VV and VH. So let's open up the VV. Okay, so that is our image, and we had talked about speckle in the previous webinar, and you can really appreciate speckle here. That's that graininess effect that you can see in the image, and we'll take care of that through multi-looking. But you can see, just visually, you can see the flow of the river, the delineation of the river, which are the really dark areas. You can see some very bright areas as well, and different tones representing either high biomass forest or areas of low biomass, probably deforestation or grazing lands. Okay, so one thing to note is that we do have two bands. One is intensity and the other one is amplitude. So intensity is the amplitude squared. That's all. And one thing to note as well is that the image is inverted. And that's because it's oriented in the same way that it was acquired. And you can really appreciate this if you go to World Map. So down here you have a series of windows, and there's one called World Map. If that doesn't pop up, you can open it by going to the menu on the top, selecting View, selecting Tool Windows, and selecting World Map here, and I'll open this window. So what World Map does, it's a Google type display that shows where your image falls within the display. Okay, so that's the coverage of your image, and this here is the city of Manaus. This point right there where I'm pointing my cursor. So note the orientation of the river, right? So that's the actual orientation, and note how it's oriented here. And that's what I meant by the image being inverted. And we'll correct for that when we do the terrain correction. We'll actually put it onto its correct orientation. So the next thing that I'm going to show you is how to display the image as an RGB. And for that, we'll go to the actual image. We'll click on the image, and we'll left click on the image, and you'll have a window pop up, and you select Open RGB Image Window. Okay, so basically an RGB image will be created with the VV band in the red channel, the VH band in the green channel, and the ratio of VV to VH in the blue channel. So we'll press OK. Okay, so there's your RGB image. And you can see, appreciate different colors here, which represents the information in the different channels. So one thing that you can do is, if you want to see the pixel values, you go to the window up here. There's in the upper left called Pixel Info. And if you move your cursor around the image, it'll give you the pixel value, which is this right here, in amplitude and in intensity. Okay, so wherever you're moving it, actually let's go here. So wherever you're moving it, it'll give you the pixel value. Okay, so you can have a feel for what the values are just by moving your cursor around. All right, so next we'll talk about pre-processing. And in this case, since this image is quite large, it's 1 gigabyte, it might take a while to go through the processing steps in a computer that's not very fast. So we will be subsetting the image. And so for that, we go up to the main menu, select raster, and then select the subset option. Okay. And what we'll do is I've defined the subset on the PowerPoint chart. And so if you take a look at this box here, the spatial subset, I've defined the scene start in the X dimension and the C start in the Y dimension, as well as the end. So if you specify these values, specify the same values to make sure you have the same subset. So it's 1548 to 2236 in the X and Y, and then 15136 to 14964. And we say OK. So if you go back to your Product Explorer, the next image here that's added onto the list is your subset. And one thing about the Sentinel toolbox is that it adds somewhere in the new name, it'll add what's been done. So here, this new image is called subset. So we'll just to keep things clean, we'll close this and then we'll open this up, bands, and let's just open up, that's our subset. Okay, so this is going to make it much more manageable to work with. It's a much smaller image. The next couple of steps are going to be focused on geometric and radiometric calibration. And the objective in performing these calibrations is to create an image where the value of each pixel is directly related to the backscatter of the surface. So we want to make sure that we correct for any type of calibration issues that are introduced because of relief or a displacement or because of antenna pattern calibrations issues. So this process is essential for analyzing images in a quantitative way and also important for comparing images from different sensors, modalities, processors, or images acquired at different times. So the first part in the pre-processing is to do the radiometric calibration. And for that, we'll go back to our Sentinel toolbox and we select the image that has been subset. So whatever you're going to do is done on the last image that was added to your Product Explorer list. Okay, so we highlight, we make sure that we're running the next process on the subset by highlighting it. And then we go up to radar, radiometric, and we select calibrate. Okay, a window is going to pop up that has two tabs and leave everything as default. So we want the output in sigma naught and we want these input parameters. You can change the directory where you're saving your files. In this case, I'm just putting things on the desktop, but you might want to create a special directory where you place your files. So you run this, and it should be, depending on how fast your computer is, it can take a couple of seconds, like mine, or it could take a couple of minutes. Okay, so once it's done, it says process completed in 13 seconds, close, and then that calibrated image is the next one here on my list. So I'll open this. And one thing to note in the file name is that it keeps tagging on whatever is done to the image. So you see here it says subset, and if you go to the end of the file name, it tags on CAL, which means calibrated. So that's an easy way to keep tabs of which image is which, and what's been done to the images. So this is now our calibrated image. Okay, and what the radiometric calibration does is it corrects many different radiometric distortions due to the signal loss as it propagates, the non-uniform antenna pattern, differences in gain, saturation. So another part of doing the pre-processing is actually speckle reduction. And we talked about speckle reduction in the first webinar. So speckle makes interpretation of the image difficult because it's a graininess, salt and pepper effect that corrupts the information about the surface. And it's very difficult to sometimes visually interpret the images, and even more difficult to do analysis on the image when you have a large amount of speckle. So there are two ways of reducing speckles. One is through speckle filters, and another one is by multi-looking the image. And we will use multi-look in this case. So the output from the previous step, which is this calibrated image, is here. We'll highlight it, and then we'll select radar, and we will go all the way to the bottom here and select the multi-looking option. And a window will pop up with two tabs again. One says input-output parameters, processing parameters. So go to the second tab, and then you specify the number of range looks and azimuth looks. So these should be the same. And let's specify 6. Okay. So as had been discussed in the first webinar, whenever you do multi-looking, or if you use speckle filters, spatial filtering, you reduce the resolution of your image. So the larger the number of looks, the more you reduce the resolution of your image. And the same goes with speckle filters. So you run that, and then that new image is placed at the bottom of your Product Explorer window. It's the last one, so in this case it's number 4. And if we go to the end here, you'll see that ML is tagged onto the file name. That means it's multi-looked. So it's calibrated and it's multi-looked. Okay, so let's close this, and that's our new image. Tremendous difference between the image, the original image, which is this one, and then the cleaned image. Okay, and if you use a larger window, we used 6 by 6, but if you use 10 by 10, it'll look even smoother. All right, so the next step here is in doing a geometric calibration. Okay, so we've done, you first do the radiometric calibration, you do the multi-looking or your filter, and if you wish to use filters, here's where you would do that. You go to radar, and you select speckle filtering, single product speckle filter, and then in the processing parameters, there are a number of different speckle filters that you can select from. The Lee filter is one of those, the most commonly used speckle filters, but you could try many other ones here and determine for yourself which one works best. One important thing to specify is the window size, and so you have a whole list of options of different window sizes. Obviously, the larger the window size, the more smoothing you do, and the more resolution you lose. Okay, so we'll, for this example, we'll stick to multi-looking, and the next step is geometric calibration. So we'll highlight the last image that was generated. And then we'll go up to the main menu and we'll select radar. We'll select geometric, and then we'll select terrain correction, range Doppler terrain correction. And what this does, it calibrates or it corrects for any sort of displacement from the terrain. And it needs a digital elevation model to do that. So if you go to the Processing Parameters tab, you'll have a number of different options here. And it says Digital Elevation Model. So by default, it uses the SRTM 3 arc second DM. But you can specify other DMs either here on the list, or if you have your own DM, you can specify that as well. So you hit run, and in this case, we're using the default. And we close this. The new image has, the file name of the new image has TC tagged onto it, which stands for terrain correction. So we've calibrated the image, multi-look terrain correction. Okay? And when you load the image, you can see that it's in a different orientation. So this is in its correct orientation now, following the river flows now in the correct direction. All right, so the next step is to convert sigma naught into dB, and this is really the way that we represent backscatter is in dB. It's a measure of power. And so the way you do that is you highlight sigma naught, either VH or VV, and then you left click and a window pops up, and then you select the linear to or from dB option. So select that. You get a window saying would you like to convert sigma naught VH into dB in a new virtual band, and you say yes, I do. And then you do the same thing for VV, so that we have both bands in dB. We say yes. And so these new bands, dB bands, are now tagged on here to the list. And so we double click, we'll display the dB bands, VV and VH. And so one thing to note too is it's always really important to take a look at the images and just get a feel for the information content for each individual one and between them. So if you look at the difference between BV and VH, there's some notable things in the patterns that you're seeing and the differences in tone between VH and VV. So that gives you an idea of the difference in the information content between the different polarizations. So to have an idea of the different dB values, we'll go up to Pixel Info, and we'll scroll around here, the image, and it gives us the intensity value right here. It's not coming up because my cursor isn't over the image, but keep an eye here on sigma naught VH dB and sigma naught VV dB. As I move around the image, you'll get a sense for those dB values, right? And if I move the cursor over the water, it's quite low. In VH, it's minus 25.55 dB. In VV, it's minus 18.725 dB. So very low. And if we move onto an area that has a brighter tone, you can appreciate how much brighter that is, on the order of minus 14 in VH and minus 8 in VV. Okay, so the next and last step here is to do a short analysis on this data set. So the first thing we'll do is to analyze the image histogram. So we'll do that looking at the lower left window here. If you don't have a window that says color manipulation, then you want to bring it up by going up to View, Toolbars, Tool Windows, and select Color Manipulation here. And that will open up down on the bottom left the window, this window here. Okay, so what this window contains is the histogram. And what we'll do is we'll identify the two peaks. And so visually you can see here that we have two large peaks. One is the land cover, and the other smaller peak here is the water. And you can see that this peak is a little higher with a VH rather than VV. Okay. So we'll select the value that separates water from everything else. And so that would be, we can move this around and kind of select that value. And so we'll say that that value is right around there, 18.85. Okay, so we'll make note of that, minus 18.85 dB. And the next step is to create a threshold to separate water and land. Okay, and the way we'll do that is we'll go to Raster, we'll select bandmath, and you'll have a window pop up. So you go to the bottom where it says Edit Expression, right here. And so what we'll do is we'll input the expression that's specified on the PowerPoint file number 32, which is file number 30, which is this one right here. So we'll actually just copy that and we'll input it right here in this expression. And we'll press OK. Oops, it didn't like the copy and paste. So what we'll do is we'll select the image there. And we say OK. And then we hit OK. And so it applies that bandmath, and it creates a new band here. It tacks it on, and that's called new band 2. And this is the result. So basically, you have a binary image where 0 is where 1 is water and 0 is everything else, and 1 is open water. And then, in order to change these colors, you go to the color manipulation window on the bottom left and select table. Okay, so you got here the 3 colors in that image. And so we'll select green for black, and we will select blue for white, and there you go. That's your open water. So you're assigning, and there's nothing there should be gray. Let's see. So we'll say yeah. So that's your image, and then okay, so and you can export it as a KMZ file by going into File, Export, selecting Other, and View as Google Earth KMZ. So it will save it as a KMZ file. And then you can open that on Google Earth. There it is. In summary, these are the steps that you need to do. First of all, the data preparation. You acquire the images, and sometimes these images cover a much larger area than perhaps your area of interest. Or you might need to subset it anyway because your processing power is not so fast. So it can be make it much more manageable if you subset the image and just work with chunks. So once you have that done, then you go through the pre-processing steps. You first do the radiometric calibration, then you do the filter application to reduce speckle, whether it's multi-looking or whether you use some sort of spatial filter. And then finally, the last part that you do is the geometric calibration. And then you can start doing your processing of the image and data analysis. And here I just showed you a basic example on how to threshold where we separate water from land. But you can run whatever algorithm you want on the image, whether it's supervised or non-supervised. And the Sentinel toolbox has different options for classification. So if you go to raster and you select classification, it's got two categories, unsupervised or supervised, and it's got a number of different options under supervised, including random forest classifier, which is actually a very powerful approach. So I encourage you to play around with these different options and determine for yourself which one gives you the best results. But I do suggest to start with random forest classifier. Of course, you'll have to go through the process of doing the training and selecting areas that you know are truly representative of your different classes. So with that, this concludes the second webinar series, and I'm open to your questions. Thank you.